Good, thank you very much. So I'm not going to go to full screen because I think this is big enough that you can see the text, correct? Okay. I'll just take a couple of minutes to tell you about a related instrument that has some different design parameters. This is called LLAMAS, which stands for the Large Lenslet Array Magellan Spectrograph. And this is a new integral field spectrograph that has a field of view of 38 by 38 arc seconds. And it's going to operate again in the optical. The Magellan telescopes are 6.5 meters. And this is an IFU that intends to cover the UV through the sort of near infrared. So it's 3,500 angstroms to 9,850 angstroms. And just since people aren't generally familiar with the operational characteristics, this is a spectrograph that's based on an array of micro lenses that feed in pupil space into optical fibers. There's 2,400 micro lenses in the array, feeding each to its individual fiber. And they project on the sky to a size of 3/4 of an arc second with 94% fill factor. I'll show you what that looks like in a minute. And just so you can see on the left side, this gives you an idea of what the focal plane will look like relative to instruments that you've heard about. And so LLAMAS at 38 by 38 is this square that you see outlined here. MUSE at 60 by 60 approximately would be this larger area. And then KCWI in its medium resolution mode is shown here in the lower left. And the requirements that we set forth for field of view for LLAMAS had to do with CGM because we wanted to encapsulate or be able to capture all galaxies that were within roughly a gas envelope size at a redshift of sort of 2-ish. And so 100 kiloparsecs is shown with this inscribed circle. And if you can see closely, I don't know how well your graphics pick it up, but the little individual circles show the sizes of the fibers projected onto the sky. So each one of those fibers will feed into one of 8 spectrographs, and those spectrographs deliver a resolution of 2200. And they go in 3 arms, which are optimized for wavelength coverage. So there's an R, a G, and a B arm. They each have VPH grisms and then optimized CCDs, which include deep depletion CCDs in the red. And then we optimize the anti-reflection coatings on those in the green and the blue. Here you see a transmission that does not include the telescope. So when you're comparing to others, you have to derate it. But you see that we paid a lot of attention to focal ratio degradation and things like that in the fiber so that we're getting extremely high throughput into the instrument as well. So this is from the telescope into the focal plane. Okay. So this is where it will sit on the telescope. It's going to be a permanently mounted facility instrument, which means that you can access it on Magellan in a 15-minute time period. So it's always on and you just rotate the tertiary. It's not only on for a fraction of the month. It will sit at one of these folded ports. It's not at an Nasmith. And so it consists of a fiber front end that sits on the rotator port. And then the spectrographs hang below it on this gantry. The reason for that, I can explain if people are interested. I don't want to go into it in great detail. But it really has to do with trying to enhance the stability of the instrument. So right now, what stage is the instrument at? So we're on track right now to commission the instrument in the summer of 2022. So the table that you see on the left here essentially is our deliverables table for what we call the flight hardware.
We can just amplify what you send out, and it would be great to get us talking more about.
Thank you. So we call this the flight hardware. Obviously, we're not going to launch this, but we're used to dealing with those terms. So you see, essentially, we have all the pieces in the lab at this point, with a couple exceptions. So we have all the lenses for the green and blue cameras, where the red ones will be here in a little over a month. In the production CCDs, we've approved those using a set of qualification CCDs, and now they're delivering 3 a month based on that design. And the camera barrels are done. We're just waiting for them to be painted. So here you see what this looks like. This shows one of our flight optical benches on the left, and this arm that you see coming off of it is a coordinate measuring machine. There's a question of how do you put all these things together in a timely fashion and ensure that they're going to be aligned quickly so you don't spend a lot of time chasing your tail. And we've invested a lot in metrology equipment so that we actually build the metrology into the hardware itself. And then we have reference points, and then we touch it to each optical surface. And then once you assemble it, because the resolution of these systems is smaller than the error budget of the optical alignment, you can align all of these. Each one of these barrels will be a spectrograph camera produced en masse, and it works quite well. I'll tell you why we believe that in a minute. Here you see the micro lens array here in a electron, or not an electron, but just a microscopic view of it. This is what the micro lens array looks like. So you can see that they individually touch each other. And as I said, the fill factor is about 94%. That excludes these little triangles between the lenses. The optical quality is very good. And we've learned how to register it to this device here, which is a set of 2,400 holes that we plug the fibers into. And then we align it carefully using these reference marks under motion control. So all the parts are basically here, and we're putting them together. How do we have confidence that this is all going to work when we do put it together? So it turns out that we already built one. So we're going to make 8 spectrographs, but we made a prototype in the lab that we finished in February of 2020 with the plan to commission it and do testing in April of 2020. Sadly, that was completely scuttled by COVID. And so that's still sitting in boxes down at the mountaintop. It's been a real disappointment for us that we can't verify its on-sky performance, but that's just been life. We did succeed in doing all the alignment and meeting every specification we had set in the lab prior to that. So here you see the front end, what this looks like on a telescope, and then this is a box with a spectrograph in it. Here you see blue and red channels of the images for an arc lamp spectrum. And then you can see the point spread functions at different locations on the focal plane, showing that. So the black ones are the optical model, the theoretical model, and then the ones next to it are the as-built, showing that it actually meets this. And that we've also got the rudiments of pipeline routines in place to extract each of these and do wavelength solutions. Here you see the extracted spectra of all the different fibers stacked on top of each other, showing that they register. This is based on Pipet, which is used extensively at Keck. But I write pipeline in quotes because without going on the sky, it's not really a pipeline. So it's a set of routines that can reduce the data, but it's not really user-friendly yet at a level that it will be once we're on the sky. The only other thing I'll say is that we've given quite a bit of thought to stability of the spectrograph and how we deal with systematics and scattered light. Particularly if you want to deal with CGM emissions, it's all about systematics and whether you're beam switching back and forth, whether the instrument is solid like a rock. We can talk about some of the technical ways to do that. We won't know until it's on the sky, but we've thought really hard about this, specifically because it's a fiber-based spectrograph. And sometimes, in principle, fibers should be better than slits for this, but in practice, that hasn't always proven true. And we've done a lot of testing for that. These are just some fun images you see. This is a microscope view of the fibers plugged into the prototype and then the backlit. So you can see that the prototype is a subset of the full IFU. So this is the light coming from the slit out through the IFU. Here you see the IFU unit. And one of the things that we've done to think about stability and systematics is that we've got a way that you can mask the focal plane and illuminate every other fiber. So you can illuminate all the odd fibers and then shift the mask and illuminate all the even fibers and use that as a way of characterizing scattered light or to do really widely spaced and get really high fidelity background subtraction with a low order background scattered light model. So we're thinking about those things in the design of the instrument. So that's all I'm going to say. I will just say that there's, it's a great team of people that's working on this. And it's a collaboration of, both the Kavli Institute at MIT and Lincoln Laboratory have been big contributors to this. Ramon Bordeloy, who's on the call from NC State, has been involved in this from the get-go. And of course, we appreciate NSF for sponsoring all this work. And I highlight also that the 3 people who are outlined in red here are the students that have been working on the project. And so thanks to this great team. So happy to take any questions about that, but appreciate your time.
All right, thanks, Rob. We maybe have time for one question. If anyone has a burning question about LLAMAS.
I have one.
Randall, go ahead.
Oh, sorry, no, nothing for me.
Not Randall. Okay. Go ahead, whoever spoke up. Apologies.
That was Chris.
Sorry, Chris.
Which NSF program did you get funding from, and what's the total cost of your experiment? And also for Johan, same questions, not NSF, but the cost.
So this was funded by the MSIP program. And because of that, oh, I forgot to mention this, but as part of this, there will be time that is competed to the US community. So I think it's 48 nights that will compete through Noir Lab. So anybody in the US community will be able to use this instrument. The total cost is about $6 million. There's some error bar on that. You know, come back to me in a year and I'll tell you. But that's about what it's going to be.
All right, great. Johan, did you want to answer that question as well?
Yeah, just to tell question. Yeah, so the cost of hardware is estimated for Blue Muse about 10 million.
All right,
and that's
perfect.
mostly funded from ESO, but and also for the consortium, like 8 million from ESO typically, and the rest from the consortium.